Okay. So in the last class, we defined a function is continuous at a point. Okay. So quickly we recall when we say a function is continuous at a point. A. So f is continuous at A. The function f is continuous at A if, so whenever xn converges to A, then f of xn converges to f of A. This is a sequence definition. If we take any sequence xn converges to A, f of xn converges to f of A, then we say f is continuous at A. And when we say f is continuous at every point, then we say it's continuous on the set J. So when we say f is continuous on J, if f is continuous at every point. F is continuous at every point. Every point A in J. Okay, and then we discuss some examples. Now, today we define another definition of continuous using epsilon delta. Okay, but in both the definitions are equivalent. We can use anything, but better is sequence definition is better. Okay, so when we say, suppose we have a function, so let f is a function from some interval j to r be a function be given. And we have to take some element a in J, we say that f is continuous at E. We say that f is continuous at E. If we take any epsilon greater than 0, for every epsilon greater than 0, there exists a delta greater than 0 such that if whenever x in J and the modulus of x minus a is less than delta implies modulus of f of x minus f of y is, sorry, f of a is less than epsilon. Okay. It's the definition of continuous at a point here. So geometrically we can see, suppose we have a function. So we take our j is somewhere. Suppose j is here. Suppose this is j is in our interval. We fix some point in j. We call that point is a. Suppose a is here. And for this point, this interval, we define function. Therefore, we have a graph of the function. Maybe look at something. Okay, and draw some like this somewhere. So this is a function f defined on this interval j. Okay. Now, when we say this function is continuous at a point E, it's nothing but, so we have to take any other point x or some x in J. Now, therefore, for the A, we have a point on the graph. This is f of E. So this is nothing but this is f of E. And if you take any other points, so this is f of x. So on the y-axis, so this is f of x. So what we need actually, so we given any epsilon, we can find a epsilon delta such that whenever x minus a is less than delta, then f of x minus f of a is less than epsilon. That means, so we need the distance between these 2 points is less than epsilon. So according to that, we have to choose the distance between these two. Okay, so this is fixed distance. So epsilon is fixed. Suppose you want distance between f of a and f of x less than epsilon. So what delta you can choose such that the distance between these x and y is less than delta, such that this is happened. So that is geometrically, we say f is continuous. So this condition, this epsilon depends on this delta. Sorry, this delta is depends on this epsilon because this epsilon is fixed. We need distance between f of a and f of x. Okay. Then what is the distance we can choose between a and x such that this is happening. So we can choose delta such that if the distance between a minus x or x minus a is less than delta, then f of x minus f of a is less than epsilon for any epsilon. So therefore, this delta actually depends on this epsilon as well as the point e. Okay, so usually delta of sometimes right delta of epsilon comma e. That means what this delta depends on this epsilon and then the point e. Okay. Suppose the delta does not depends this point, only depends on epsilon, such a function is called uniformly continuous. Okay, that means what? A single delta works for all point, that is uniformly continuous, but continuous nothing but for each point we have a different delta, maybe. Okay, so this is the meaning of continuous. But anyway, you just note that the definition. But better you use the sequence. But anyway, both the definitions are equivalent. Okay. Now, actually, what we have to estimate, suppose we have to do a function is continuous, you have to estimate this inequality, that is modulus of f of x minus f of a is less than or equal to c suffix a, some constant. Okay, this is function of e into modulus of x minus a. So suppose you want to prove f is continuous at a, you try to estimate this as less than or equal to some function of a into this modulus of x minus a. Okay. This e is nothing but function of e. So to prove f is continuous, we have to estimate this x minus a modulus of x minus a into some function of e. Okay, that is our aim. Okay, anyway, so we can saw some examples. Very important example, Thome function. Okay, so the function is called Thome function. Thome's function. It's a very important function. So it's a function defined. Okay, Thome function. So the function is defined by f is a function from R to R. Okay, so f is a function from R to R is defined to be f of x equal to, so for irrational we define 0, that is if x is irrational, it takes 0. If x is rational, then rational is of the form p by q, right? Then we define 1 by q, provided the GCD of p comma q should be 1. Okay. So for irrationals, it takes 0. For rationals, it goes to 1 by q, where q is the denominator of the rational part. So this function is called the Thome function. We prove that this function continues only at the irrational point, discontinuous at the rational point. Okay. So f is continuous at all irrational point. F is, it's very important function. F is continuous at all irrational points, irrational numbers, but discontinuous at all rational points, and not continuous at the rationals. Not continuous at any rationals. In the point, okay, better we define the function is domain is open and zero. So that is important thing. Not to R to R. So in this interval we have rational and irrational. Okay, so any points of this open and zero. Okay. So we prove this using this estimation. Okay, we can skip that proof. You can go through the book, you will get the proof. Anyway, so this Thome function is an example of a function which is continuous at all irrational points, but discontinuous at all rational points. Okay, so what about the converse? Can we have any function which is continuous at all rational points, Okay, actually continuous, not continuous at any irrational points. Now, naturally we can ask the question, suppose can you have a function which is continuous at all rational points, but discontinuous at irrational points? Such a function does not exist. Okay, so that is very important point. Note or remark, there is no function which is continuous at all rational and it is continuous at all irrationals. Okay, so that does not exist. That does not exist a function which is continuous or at all rational points and not continuous at irrational point and not continuous at all irrational points. Okay, such a function does not exist. Okay, it's a very important actually example. If you go in interview, they will ask such a function exists or not. Okay. Okay, it's very difficult to produce that function, but such a function does not exist. We can prove. Okay, now, so the Thome function is an example of a function which is continuous at all irrational, but not continuous irrational, but and there does not exist any function is continuous at all rational and discontinuous at all irrational. Now, these are all important thing in that definition of continuous part. Okay, now we move to the applications of this continuous function. So the important thing is intermediate value theorem. So first, a very important application of continuous function, intermediate value theorem. So suppose we have a continuous function on the closed interval 0, 1. Okay. So what is the statement of the theorem? Let f is a function from the closed interval a, b to R be a continuous function. Be a continuous function. Therefore, every element of this domain we have a pre-image or we have an image, right? So, continuous function such that then what is the relation between this f of a? Because a is an element here, therefore f of a is somewhere here. Similarly, b is here, therefore f of b maps somewhere. Suppose the relation between f of a and f of b is f of a is negative and f of b is positive. Then this has happened, then definitely there is an element in the domain C such that C maps to this 0. Okay, so then there exists C. There exists C in the open interval a, b, because already a, b are maps to something, right? So there is a C in between open interval a, b such that this C maps to 0, such that f of C equal to 0. Okay. Right. So it's actually nothing but we have a root. F of C equal to 0 means what? C is a root of the function or solution of the function. So actually what is a geometrically we can see. Suppose A is somewhere, B is somewhere. This may be positive or negative. It's not a matter. But suppose we assume that A is here and B is here. This is our domain of the function. Suppose f of a is given that negative value. So for f of a, we have a negative and f of b is positive. Therefore, f of a takes some negative value here and f of b is positive. Therefore, somewhere here. Okay, and we know that the function is continuous. Therefore, we start from this point. Anyway, it reaches to that point. Definitely, this function should cross the x-axis. Okay, because it's a continuous function. Starting point is this f of a, and this end point is f of b. Since the function is continuous, it passes through that point, passes through the point on x-axis. So this point actually our c. So therefore, at the point c, the function takes the value 0. Okay, that is the thing. So suppose we have 2 points. Let's take the opposite value. One value f of one value is positive, another value is negative. Then definitely this function vanishes at one point in this open interval. Now look at this, c lies in this open interval a comma b. Okay, so that is the intermediate value there. So suppose instead of 0 here, suppose we have some other number k. Then again there is a c such that f of c maps to this k. Okay, that is actually another thing. Now we call as a standard version, intermediate value theorem of standard version. Suppose f of a less than some k less than f of b. Again, f is a continuous function defined on closed interval a comma b. Then there is a c such that f of c equal to a. Another theorem. That theorem is called, again that theorem also intermediate value theorem, but standard version. Standard version. That is generalized version. If we take the specific value k equal to 0, we'll get that previous theorem. So standard version of intermediate value theorem. Simply we call IVT, intermediate value theorem. So what the theorem says again, suppose we have a continuous function g from closed interval a comma b. That is very important. The domain should be closed interval a comma b to r be a continuous function. Suppose we have a continuous function defined on the closed interval a comma b such that what is the relation between this f of a and f of b? So such that suppose g of a strictly less than some k or lambda something is less than g of b. That is lambda strictly between g of a and g of b. Then the theorem says then there exists some c. There exists some c from the open interval a comma b such that this c maps to that lambda such that g of c equal to lambda. Okay. So same thing. So this is actually corollary of the previous one. So then we have to use the, so suppose assume that we have a proof in intermediate value theorem. This theorem we know the proof. Okay. Now how to prove this one? So which continuous function you can take? So what is the f of x now? Here can anyone guess? We are going to use the previous theorem, but if previous theorem says we have a continuous function f such that that f of a less than 0 less than g of a, we know that there is some c such that this maps to 0. Now we are going to use that theorem, but using this condition g, how we can construct a new function, that new function satisfies the previous condition, previous theory condition. Can anyone? So using this condition, you have to construct a new function. That new function actually satisfies the condition f of a strictly less than 0, strictly less than f of b. And we can, so we know this, then previous theorem, there is a c in open interval a comma b such that f of c equal to 0. Now what the function you can choose? G of x minus lambda. Since lambda is a constant function is continuous, g is a continuous function continuous, subtraction of two continuous functions is continuous, therefore f is continuous. Now in this inequality, you got to subtract lambda both the side. All the side you have to subtract this one. Therefore, what will get? G of a minus lambda less than 0 less than g of b minus lambda. But we define f of x nothing but g of x minus a. Therefore, g of a minus lambda is nothing but f of a less than 0 less than f of b. Now, use the previous theorem. So, there is c in open interval a comma b such that f of c maps to 0. But what is f of c? G of c minus lambda. You can take lambda to that side, we have our conclusion. So just to correlate the previous one. Okay. Any doubt in this? Okay. Now, so what is this? There are some applications of this intermediate value theorem. So intermediate value theorem application. Okay. So we discuss some examples. Exercise 1. Suppose we have an interval J. J is a subset of R, B an interval. Maybe it's a closed interval or anything, but interval. So interval, and let we have a function f from J to R. Be a continuous function, CTS, continuous function. Okay, and what is the condition? We have f of x is non-zero for any point. F of x always takes non-zero point for any point in the domain. Show that either f should be positive or x should be negative. Cannot be both on the interval J. So how to prove this one? So what is the given that we have a continuous function. That continuous function never takes 0. That means what? What can you say about that function? That functions take never 0. They never take 0. That means what? The function does not cross the x-axis. Suppose a function crosses the x-axis, then we have a solution. Okay. So therefore, so clearly, suppose this is not happened. We have to prove that either f is positive or f is negative. Suppose both case happen. Suppose we have both negative and positive. Suppose we have 1 point take negative value, 1 point take positive value. Then since it's continuous, therefore we have like a function. Therefore, at this point C, this takes 0, but which is contrary to our assumption that f of x never 0 for any point in the domain. Therefore, either f should be positive or f should be negative, not both. If it is both, we have a 0. We have a solution for f. But in the assumption given that f of x not equal to 0 for any point in the domain. Okay, so it's a simple proof. Now, second one. Suppose again we have a function, continuous function from R to R. We have R to R continuous function. Taking values in Z are rationals. So this function maps to either integer or rational points, but it is continuous. Then what can I say about the function? Okay, then show that. Okay, then what can you say about f? Then f is dash. That means what is a continuous function? Keep in mind, it's a continuous function, but it takes the values are either integers or rationals. Therefore, this f does not take any values in Q complement. Okay, now what can you say about this function? Okay, should be constant, right? Because that constant should be either integer or rationals. Therefore, it's a constant function. That is the only possible. because this is a discrete set. Z is a discrete set. Q also almost a discrete set. That means what? There is a gap between any 2 points. That is a discrete set. But the function is continuous. So we can draw the graph without removing our hand. But we assume it is given that it takes only integers or rationals. Okay. So therefore, the only possible is constant function. This function satisfies our assumption that constant function is continuous, and constant, if you take some 5 or something, is satisfy our condition. Suppose if you take f of x equal to 5 for every x, then this function satisfied our assumption. This is continuous because constant. All points takes an integer. Okay. So a continuous function takes the discrete values. Then the function should be constant function. If it is not constant, okay, so we have to prove that this is constant, okay. Suppose not constant. So constant means what? Every point maps to the same point. That is means what? F of x equal to f of y for any xy. Any xy in the domain R. So that is a constant function. Everything maps to same value. That is constant. We got to prove that that function is constant. Suppose not constant. Then what will happen? Suppose f is not constant function. Suppose f is not constant. So not constant means what? So there is a 2 points whose images are not equal. So there is a 2 points x comma y in R such that these 2 points maps to different values. Because constant means what? Everything same value. Not constant means what? At least 2 elements, the images are different. Okay. Now, so the images are different. Therefore, either f of x is strictly less than f of y, because these are real number. We can compare it. Okay. Or f of x is greater than f of y. There are only 2 possible, because by law of trichotomy, given any two real number, either both are equal or less than or greater than, it is given that is f of x not equal to f of y. So therefore, either f of x is less than y or f of x greater than y. Suppose we take this case, then what will happen? Look at the graph. So without lot of assuming generality, we assume that x is here and y is here. Now look at this interval now. Okay. So, but the given function is defined on R to R. But we can restrict this function is our small domain x to y to R. So maybe that function is we call G, that G is a restriction of f. Otherwise, simply we can say f restriction to this interval x comma y. Still that function is continuous. Okay. Now, therefore, the function f is continuous from R to R. Therefore, this function still is continuous in this particular interval. Okay. So, okay, now is given that suppose we can take this case, f of x is smaller. Okay, maybe we can take here. This is f of x value. So f of y takes something should be bigger than f of y. Therefore, this is our f of y. Okay. You can take negative side also. F of x you can take negative side also, but it's no need. You can take anything. Okay. So now, since f is continuous, therefore we can join these 2 points via some curve. Now, what is the contradiction we get? To look at that, is take only integers and rationals. But, so actually look at this. So this is our range set. So in this range set, we have rationals and as well as irrational. So if you take any irrationals here, if you draw here, we takes the, so this C takes the irrational value. Okay. So it is a contradiction. So therefore, this function should be constant. If it is not constant, we get a contradiction to our assumption. Because the continuous function takes only values in Z or Q. This is another example. Now, the third, one more example of this intermediate value theorem. Suppose we have a continuous function, non-constant continuous function, from closed interval a comma b to R, be a non-constant continuous function. Non-constant continuous function. Then the image of this interval is uncountable. Then f of the interval close to a comma b is uncountable set. So that is, it contains infinitely, that is uncountable number of points. So it's clear, right? So why? Since it's a non-constant function, therefore at least two elements in x comma y in the closed loop a comma b takes the different value. F of x not equal to f of y. Because it's non-constant, at least 2 points maps to different values. But the function is continuous. Now look at the thing. Suppose we have a point is here x. Anyway, this is AB. But we don't know about other point, but at least we have a x and y without lot of generality, we assume that x is smaller than y. For this interval, if you consider this interval, now f of x not equal to f of y. Suppose we take f of x is here and f of y is suppose here. Okay, this is f of y and this is f of x. Since f is continuous, therefore you can draw in the line via some graph. Now look at this. What is the image of this interval? Actually, it takes this portion and then this. So this is our image of this interval, particular interval x comma y. So this x comma y is a subset of this a comma y, right? So therefore, if you consider the a comma b, maybe here for range of a comma b may be bigger than this one. Anyway, this f of a comma b contains this portion, this length. So maybe this actually f of x to f of x. Okay. So this contains f of x to f of y interval. Okay, every interval is an uncountable set. Therefore, this set contains an uncountable set. Therefore, this is an uncountable set. Okay, why is an uncountable set? This contains infinitely many points in the line. So within this interval, we have uncountable number of points. Therefore, continuous image of an interval is an uncountable set. So this is also one of the useful of intermediate value theorem. And then if you take any odd degree polynomial with a real coefficient, it has a real root. So you already stated that thing. Okay. Maybe I state that theorem, but you already know that theorem. If you take any polynomial with odd degree, at least one a real root. Any polynomial of odd degree, because already we know that complex roots are always appear in pair. If z is a root, then z bar is also a root. So therefore, if you have any odd degree polynomial with real coefficients as roots, as a one root, real coefficients as a real root, real zero or real root. Okay, because we know that complex conjugator appear in pair. Therefore, we have always even number of pair, even number of roots for a complex number. But it's odd degree. Therefore, we have at least one real root. It's just, simple. Okay. Either we can use this theorem, what is the intermediate value theorem. So that means what you have to find the 2 points. The values are positive and the negative, opposite sign. Then we have a root in between these two. Okay, that is the applications of this one. Now, one more theorem is fixed point theorem. So fixed point theorem, fixed point means what? Suppose f of c maps to c, then c is called the fixed point of the function. Okay, so f of some c equal to c. Okay, then c is called a fixed point. That function is fixed. Yeah, c. Okay, c is called fixed point. fixed point of the function f. Okay, f is continuous function. Okay, now can anyone tell me what is the fixed point of this function f of x equal to x plus 1? So which points maps to the same thing? For what values of x maps to x? So that means what you have to consider f of x equal to x. So but what is f of x? X plus 1. We can cancel x, we get to 1 equal to 0. That is not possible. Therefore, there is no fixed point for this function. Even this function is continuous function, but this have no fixed point. This function does not have any fixed point. But if we consider this function f of x equal to x minus 1, now alter this again. So this we need this is equal to x. Therefore, we can cancel x again. We get minus 1 equal to 0. That is not possible. Therefore, again this function have no fixed point. Okay. Now, if we take f of x equal to x, then everything is a fixed point. 1 goes to 1, 2 goes to 2, 3 goes to 3. So all the points are fixed point. All points are fixed point. Okay. Now, what is the fixed point theorem says? When the function, continuous function, have a fixed point. Is a theorem called fixed point theorem. Fixed point theorem. So when a continuous function defined on the closed double a comma b to closed double a comma b have a fixed point. So if you take any continuous function f from the closed double a comma b to the same set closed double a comma b, a comma b. So if you take any continuous function, then f has a fixed point. That is, what is the meaning of this? There exists some c in the closed double a comma b such that the c maps to c. So any continuous function from closed double a comma b to closed double a comma b, it always have a fixed point. But we don't know how many fixed points are there, but this theorem says at least one fixed point should exist. And maybe there is some standard Brouwer fixed point theorem, contraction as well, there are something there. So if it is the function is contraction function, then it has a unique fixed point, but the domain should be complete. Anyway, you all studied it in the functional analysis course. Okay, now another theorem can go. Weierstrass theorem, we already found that if you take any continuous function, the function should be bounded. So when we say a function is bounded function, okay. So definition, suppose we have a function f from R to R something, okay, or J to R. Suppose we have a function J to R, okay. So we say that f is bounded. So when we say a function is a bounded function, if the modulus of f of x for all x is bounded by some positive number m for all x in the interval j. So that is, there exists a m greater than 0 such that all the values of the image of things should be less than or equal to some positive numbers. Such a m exists, then we say f is bounded function. And Weierstrass says, if you take any continuous function from domain is closed to a comma b, that function always a bounded function. Okay. Theorem. The theorem is called Weierstrass theorem. Weierstrass theorem. So Weierstrass theorem says, if you have a continuous function from closed interval a comma b to R, closed interval a comma b is very important. If the domain is compact set, that is closed interval a comma b is continuous, then f is bounded. So the domain is closed interval a comma b is very important. Suppose if you omit that condition, even the function is continuous, but the domain is not closed interval a comma b, then the function need not be bounded. So what is the example for that one? If we take, I'm considering the example, f is defined on open interval 0 comma 1. So but we need a closed interval. Suppose if you remove that condition, I take the domain is open interval 0 comma 1 defined by f of x equal to 1 by x. Since x never takes 0 because we take open 0. So this is a continuous function. Clearly this is continuous. But this is unbounded. Why? Since in particular in the 0 to 1 we have a 1 by n. So all the 1 by is lies in this interval, right? So what is f of 1 by n? 1 by 1 by n is nothing but n. So n is increasing, this is increasing. So therefore we cannot find a unique m. This is happened. Okay. Therefore this is a continuous function but not bounded. So therefore the domain of the function should be closed interval a comma b is very important. If you remove that condition, the function need not be bounded. Maybe this function is unbounded function. So, okay, next thing, there are some more theorems are there. So we say, when we say a function is a monotone function, so increasing, decreasing. When we say a function is increasing, when we say a function is decreasing. Next, monotone functions. Monotone functions. So first we discuss about what is strictly increasing function. So definition 1. So we say a function, we say that the function f from the interval j to r, so need not be continuous, just any function, okay, where j is a subset of r, is strictly increasing, is said to be strictly increasing. Strictly increasing if you take any two points x comma y in the domain with the x is strictly less than y, implies f of x also strictly less than f of y. If whenever x less than y, then f of x less than f of y for all x comma y, then we say the function is strictly increasing. Suppose conclusion that f of x greater than f of y whenever x less than y, that function is decreasing function. So we can define, similarly we can define decreasing. So if you take any 2 points x comma y in the interval with the x is less than y, but f of x is greater than f of y, then we say f is strictly decreasing. Okay. F is strictly decreasing function. Suppose sometimes is greater than or equal to, or here also less than or equal to this, then we omit, we have to remove that strictly from the definition. But if it is strictly less than, then we say strictly increasing. Otherwise, we say just increasing or decreasing function. Okay. Now, suppose a function either increasing or decreasing, or either strictly increasing or either strictly decreasing, then we say it's a monotone function. So, monotone function is either increasing or decreasing, strictly increasing or strictly decreasing. So, a monotone function is either increasing or decreasing. A function is said to be monotone function if either is strictly increasing or strictly decreasing, but not both. Either strictly increasing or strictly decreasing function. Okay. Now, when the continuous function is monotone function, so that is a theorem. So if the function is continuous and 1, then the function is monotone function. So maybe that is either increasing or decreasing. That is a theorem. So already you know what is a 1 function. Is different elements maps to different thing. So the theorem says, suppose we have a continuous function defined on some interval j. So let j is a subset of R be an interval, any interval. And suppose we have a function f from j to R. So let f is a function from j to R, be a continuous function. Be a continuous function and one-to-one function and one-to-one, one function. Then f should be monotone. F is monotone. That is either increasing or decreasing, but not both. This is a very important thing. So a continuous one function should be monotone function. Now, what about continuous image of an interval? It's an interval only when the function is monotone function. If your function is monotone and continuous, then the image of interval is also an interval. So in general, image of an interval need not be an interval. Even for continuous image of interval need not be an interval. Okay, because for example, suppose we define is a function from closed interval 1 comma 2 to some r, defined by f of x equal to I take some constant function 5. So this is a constant function. We know this is continuous. Then what is f of this 1 comma 2 is just a singleton 5. But singleton 5 is not an interval. But when this continuous image of interval is an interval, only when the function is monotone function. But this is not monotone. It's just a line. Okay, y equal to 5 line. It's neither increasing nor decreasing. So that is theorem says if we have a monotone function, so let j be an interval and f is a function from j to r be a monotone. Monotone function, assume that the image of j is some I. Okay, it's an interval. Suppose the image is an interval. Suppose the image of the interval is j is an interval, then f should be continuous. The only possible f is continuous. Okay. Otherwise, that is not. So, any doubt in this? Now, one more theorem is inverse function theorem. So the theorems are very important. You have to use this theorem to solve the problems. So the next theorem, the theorem is called the inverse function theorem. So when a continuous function have an inverse function theorem. Okay. That is when f inverse exists and that should be continuous. Suppose we have an increasing function. Let f is a function from j to r be an increasing function. Be an increasing function. Increasing not only function is a continuous function. That is very important. Increasing continuous function. Continuous function on the interval and an interval j. J is an interval. Okay. Then the conclusion is f of j is an interval. So that is a increasing continuous image of an interval is an interval. But in general, continuous image of an interval need not be an interval. Just now we take the constant function. The image of an interval is not an interval, but if the function is increasing, then the continuous image of an interval is an interval. That is the first part of the theorem. Then we define the restrict the function f j to only take the image of because just to take the image in the code of this function is a bijection function. We can easily show it's a 1 1 and on 2. So clearly this is bijection. It's a bijection and the inverse. So once the function is bijection, then we can talk about the inverse. Then and the inverse function. Inverse function f inverse from f of j to j. Domain and codomains are interchanges. Now this function is continuous. Okay, but in general, even f is continuous, the f inverse need not be continuous. Even so, when this f inverse exists, only when f is bijection. If f is not bijection, then that f inverse not exist. Even that f inverse exists, f inverse need not be continuous. But if you take that f of j is an interval, then this is happen. Okay. So just go through the thing. So what is the statement inverse function theorem? Suppose we have a strictly increasing continuous function on the interval, then the image of that interval is an interval. And if you consider the function, we have to restrict the codomain R to f of j because that is the image, that is the range of f. Okay, therefore we omit all other elements. So only take the images, then the function become a bijection. Why this is bijection? So if you take any function, if you take the codomain is only take the range, then the function is onto function. But why this is a one function? Because of its increasing function. So therefore this should be 1. So therefore this f is become a bijection. So once f is bijection, then f inverse exists from f of j to j. And even that function also continuous. That is inverse function theorem. Okay. So there are some more examples are there. Okay, we start the limits in the next class. Okay, thank you. If you have any doubt, you can ask.